Welcome, dear viewers, to this new video, in which we will learn step by step how to build this robot, which can be controlled via Bluetooth and a smartphone app. You can control the movement in real time, and positions can also be saved and replayed for automatic movement. We will start by building the robot, then connecting its components electrically. After that, we will program the Arduino controller on it and then develop an application using the MIT App Inventor tool to control the robot remotely. So don't forget to like the video, leave your opinion in the comments, and subscribe to the channel. In the first stage, I designed each component of the robot arm using the Autodesk Inventor program. This software allows computer-assisted design with accurate 3D modeling, ensuring that the components are designed perfectly to fit the servo motors. SG90 and MG996 are servo motors were chosen based on their balance between weight, size, and torque capabilities. SG90 motors are ideal for smaller arm joints due to their compact size and sufficient precision, while MG996 motors are used for the base and other areas that bear high loads due to their high torque capacity. To support this motor in this joint, I designed these openings to which a rubber band will be attached. This will support the motor when carrying the robot with a heavy load. Additionally, I designed the possibility of using this bearing, which will help ensure central circular movement. It is optional, and you can choose not to use it if you wish, but it is preferable to use this bearing. I also added these cylindrical rims that will help ensure central movement in the joints. I applied this design to all the joints. After I finished designing the robot, I converted the parts into printable pieces with a 3D printer and started printing them. As you can see, these are the components. I then began assembling the servo motors by mounting the first servo motor on the robot arm base, using suitable screws. This motor acts as a pivotal rotation point for the entire arm structure, allowing for basic movement. Next, I connected the servo horns to each joint using the small wheels that come with the servo package and fastened them with screws from the package. Then I installed a bearing to facilitate smooth rotational movement between the base and the upper rotating part of the arm. You need to press this bearing vertically into its place until it is fixed. Then, I connected the upper part of the base to the base using a screw from the servo motor package. You need to press vertically and tighten the screw. Following this, I installed the servo motor for this joint and used appropriate screws for that. I made sure to tighten the screws firmly. I then connected this link of the robot to the upper part of the base in the same way, using the screw from the servo motor package and tightening it securely. After that, I added the servo motor for this joint and tightened the screws firmly. I also installed the SG90 servo motor for this joint in the same way, tightening the screws from both sides. Once that was complete, I fixed the horn of the servo motor, which connects the servo motor's movement to this part, and tightened it with 2 screws. Due to the length of this link, I cut its sides so that I could assemble the 2 links together. This way, I added the screw to connect these 2 links. I tightened the screw and tested its rotational movement. Then I added the SG90 servo motor for this joint, which controls the gripper. Using the same method, I tightened its two sides with screws. Then, I added this link that will connect the servo motor with the gripper and tightened it in the same way, cutting its sides. Caution should be exercised when cutting to avoid injury or other accidents. After completing the cutting process, I assembled the gripper with its corresponding link. In the same way, I attached this link that connects the part of the gripper to its corresponding servo motor. The gripper will also be cut from one side and then assembled to match the corresponding part. Next, I added the SG90 servo motor and tightened it from both sides in the same way. Then, I connected the servo motor shaft to the gripper to control its rotational movement. So when the servo motor rotates, the gripper opens or closes. Now, I will assemble the entire robot by assembling this joint. Afterward, I will mount the robot on this wooden board to ensure its stability during movement. After finishing the mechanical assembly of the robot, I connected it electrically using this diagram. I connected all the motors to the servo motor driver board and also connected the board to the Arduino board and powered it electrically. After completing the mechanical and electrical assembly of the robot, I will now program the Arduino board for interactive control. This is the Arduino code that controls a robot arm with 6 degrees of freedom via wireless communication using the HC05 Bluetooth module. This code allows you to save multiple positions of the servo motors for the arm and run them sequentially or in a continuous loop. I will now give a detailed explanation of this code. First, I added the libraries. We have the wired.h library, which facilitates communication via the I2C protocol between the Arduino and the PCA9685 servo driver board. Then, we have the Adafruit PWM servo driver.h library, which is used to control the PWM signals sent to the servo motors through the PCA9685 board. We also have the software serial.h library, which enables serial communication via digital pins and is used here to communicate with the HC05 Bluetooth module. After adding the libraries, I defined the constants. We have number servos, which determines the total number of servo motors in the robot arm, and max configurations, which defines the number of positions that can be stored in memory. Then, step delay specifies the delay between each step of the servo movements to prevent sudden movement of the servo motor. Step size defines the degree of movement for each step to ensure smoother transitions. Then we have servo channels, an array that defines the channels the servo motors are connected to in the PCA9685 controller. Afterward, I defined the storage structures. We have saved configurations, a 2D array that stores the PWM values for each servo motor in each position. Then, current servo positions is an array that tracks the current positions of the servo motors. We have config count, which keeps track of the count of saved positions, and is playing, a flag indicating whether the system is currently running the saved movements. Loop playback is a flag that determines whether playback should be repeated in a loop. Stop playback is a flag to stop the playback process, and current pose index tracks the current position being played. Finally, this initialized flag checks whether the initialization has occurred. I then defined the pins that will communicate serially with the Bluetooth module and created a PWM object. In the setup function, I initialized the serial monitor to monitor and debug information and errors. Then, I initialized the Bluetooth connection at 9600 baud and set a PWM frequency of 60 Hz, which is suitable for controlling servo motors. After initializing the motors, they are moved to the middle position to avoid any sudden jumps when the system starts. In the loop function, incoming data is checked via Bluetooth and processed, with commands such as save, play, stop, or reset positions being handled. Here we process the incoming commands. The letter S saves the current servo position as a pose, while the letter R resets all saved positions. The letter ST stops the playback of the saved movements, and loop on OFF turns on or off the repeat playback of saved positions. Other commands involve specific servo positions. I then define the functions called in the loop. We have the process last value function to handle commands involving specific servo positions, translating the incoming angle from 0 to 180 degrees into the PWM value to move the servo motor. The move to position smoothly function moves the servo motor smoothly to the desired position, avoiding sudden movements. The save current pose function saves the current positions of all servo motors in the save configurations array and increases the count of saved motors. Then, start playing poses initiates the playback of the saved positions from the beginning. The play next pose function plays the next saved position by setting each servo motor to its stored position. The play poses in loop function continuously plays all the saved movements in a loop until a stop command is received. Finally, stop playing poses stops the playback of the current positions, and the reset function deletes all saved positions and resets the system for a fresh start. After explaining the Arduino code and uploading it to the Arduino board, I will now explain the robot arm control application. This user interface is designed to control a 6-degree of freedom robotic arm wirelessly through Bluetooth. I developed this application using the MIT App Inventor tool. If you're interested in more lessons about this tool, you can visit the videos I made about it. The application allows users to control each joint of the robotic arm in real time, save different positions of the arm, and replay these positions either once or in a continuous loop. The application starts with a feature to connect to a Bluetooth module attached to the arm, enabling wireless control. Then, there are sliders to control the servo motors, with 6 sliders corresponding to each of the 6 joints of the robotic arm. When these sliders are moved, the location data is sent in real time to the corresponding servo motor, allowing precise manual control of the robotic arm's movements. The application also includes buttons to save positions, play saved positions, reset saved positions, and stop any continuous playback. There is also a toggle for repeated playback, allowing the saved movements to be looped. When enabled, the robotic arm will continue to repeat the saved movements until the loop is stopped. It also displays the current number of saved positions to help the user keep track of their configurations. I will now explain the blocks of this application. First, there is a block that initializes a global variable called receivedText, setting its initial value to 0. This variable will be used later to store and manage the data received from the Bluetooth connection. Then, before selecting a Bluetooth device, the code is executed when the user selects a Bluetooth device from the list. ListPicker1.Elements is populated with the names and addresses of available Bluetooth devices using the Bluetooth client addresses and names method, allowing the user to select the available Bluetooth device to connect. After pairing, this part is executed after the user selects the Bluetooth device from the list. An attempt to connect is made, and if successful, the text connected is written, and the background is colored green in label1.text. If the connection fails, the background is colored red, and not connected is written. The toggle for the repeat switch controls whether or not to play the robotic arm positions in a loop. If a specific position for the servo motors has been saved and this switch is activated, the robot will keep repeating the same movement. The slider position blocks deal with changing the position of the sliders that control the servo motors. For example, Slider 1 and Slider 2 send the servo motor position when moving the slider. The application sends the new position value via Bluetooth, specifying the servo number and the position value. Then, The stop button block is executed when the stop button is clicked. The Bluetooth connection is checked, and a symbol is sent, interpreted in the Arduino as stopping the playback. The save, play, and reset button blocks form the core function of the robot arm control application, providing an interactive and easy way to control the robotic arm wirelessly via Bluetooth. And so, we reached the end of today's video. I hope you enjoyed and benefited from it. Don't forget to like the video and subscribe to the channel to stay constantly updated with all the latest.